Hello everyone. Today in this class we are going to learn equation of an alternating quantity. So before starting this derivation we need to understand Faraday's laws of electromagnetic induction. There are some requirements for Faraday's laws of electromagnetic induction, like firstly we need a conductor, second one we need a magnetic field, and third one, which is very important, the relative motion between the magnetic field and conductor. When we observe these three, then we can expect an EMF in that particular conductor. Okay, so this is Faraday's laws of electromagnetic induction, and this is about the first requirements. Okay, so now let us see these 2 points, okay, which are very important in our derivation. Okay, so you can see this is plane of magnetic field. Okay, you imagine this is a plane of magnetic field and this is a plane of motion. If they are parallel, that means they are making some 0 or 180 degrees. Okay, so then there won't be any kind of flux cutting. So in this state, the EMF in that particular conductor is 0. When we come to the second case, so if this is a plane of magnetic field and this is the plane of motion, so here in this case, so both planes are making 90, angle 90. So in this case, the maximum magnetic lines of forces will be cutted by the conductor. Okay, so at this point we can observe a maximum induced EMF in that particular conductor. So these 2 points are very important. When planes are parallel, okay, that is they are making 0 or 180 degrees, there won't be any kind of EMF generation. While it is making some 90 degrees, then it will be some maximum value of EMF can be observed. Meanwhile, you're having different kinds of angles, you can observe different magnitudes of EMF but not maximum. So you can observe the maximum value only at 90 degrees. That means the plane of magnetic field and plane of motion should be perpendicular to each other. Now let us consider a single turn two pole alternator. So that can be observed in the first figure. So here the coil AB. So this is coil A and coil ABCD. Okay, so this coil is rotating with a constant velocity in the magnetic field. So where is the magnetic field? So this is a magnetic field. So north pole and south pole. So we have to remember this point that magnetic field always flows from north to south external to the magnet, but internally it will flows from south to north as it is a closed path. Okay, right. So now what is happening? We have considered one instant. Okay, so this is the instant at which the velocity is v. And before starting this derivation, we need to understand certain factors or elements. Okay, so we need to understand what do you mean by flux density. Okay, so flux per unit area is nothing but flux density, that is measured in Weber per meter square, and active length of the conductor. So there is a difference between length of conductor and active length of conductor. Okay, active length means the portion of the conductor which is actually participating in cutting the flux is nothing but our active length. Okay, now radius. So radius of circular path. Okay, so r means it's a radius, right? So it's a circular path traced by the conductor and which is measured in meters. Okay, and one more parameter is a angular velocity, that is omega. Okay, so angular velocity means if we consider any kind of body that can be of any shape, whatever it may be, if it is moving with respect to time means it is making some angle. If it is moving means it is moving with certain velocity. Okay, so that quantity can be related as angular velocity. Okay, so we'll discuss that angular velocity in coming videos. And one more term is a velocity. So v, so v is a linear velocity of the conductor in meters per second. So now we coming back to this point. So at this point, what is the linear velocity? That is v. Let me erase this one once. Okay, right. So here is velocity component. Okay, it is having x and y components like this. Okay, so it is making an angle theta over here, you can observe. Okay, so whatever the portion that we are observing here, it was elaborated in the second figure. Clear? Now, so this point is there, no? So this point is A, right? And this point is origin O, right? Right. Now, so see here the angle is theta, right? So here is the angle theta. Okay, so based on our mathematics, if here the angle is theta, so here the angle is also theta. Okay, so we just projected into x and y components so that we are getting these lines. Okay, so x and y components. All right, now if here the angle is theta and is a right angle triangle, right? So here the angle is 90. In a triangle, the total angle is 180. So based on that concept, so here the angle is obviously 90 minus theta. Okay, so you should understand these angles. Okay, so once you got this idea, it will be easy. Okay, so from this triangle, if we apply cos theta and sin theta calculations, then this side will be considered as v sin theta and this component will be called as v cos theta, x component and y component. Okay, so since these two triangles are similar triangles, these two sides are equal and these two sides are equal. Okay, so here we're not going to use this point, but anyhow I'm telling you. All right, now in the first slide itself, what we have discussed, if the plane of magnetic field and plane of motion are perpendicular with each other, then EMF will be maximum. Clear? So now here what you can observe, north to south, how the magnetic field is flowing, from top to bottom it is flowing. That means in this way magnetic field is flowing. Okay, so now according to our coil direction at this instant of time, okay, so now which component is perpendicular to the magnetic field? Which component is that, V sin theta or V cos theta? Obviously, you can observe this is the V sin theta. So this is the component which is perpendicular to the magnetic field of magnetic lines of force, okay, or magnetic field itself. Okay, so this component V sin theta is the only responsible part which is leading to the induced EMF in that particular coil. Okay, so according to Faraday's law, what we can say, E equal to BLV sin theta. You can observe here. So when this theta becomes 90, okay, so when theta becomes 90 only, why you are getting the maximum value? Because sin theta has a limit of -1 to +1. So sin 90 is 1. So it got its maximum value. So obviously the corresponding coefficient, that is BLV, is going to be the maximum value. So that's why, so E equal to, you can observe here, E equal to BLV, which is itself is a maximum value. Okay, so from this equation what we can write, E equal to E max sin theta. Similarly, we can derive the relation for the current also, alternating current also. As simple as that, I equal to I max sin theta you are going to get if you do. Okay, so this is how we need to understand the equation of an alternator. I hope you understand. Thank you.